Okay. In a random sample of bags of candy, it was found that 41% of the pieces contained chocolate. So 41% of the pieces of candy contain chocolate. That means that the probability of containing chocolate is equal to 0.41. That's given. It was also found that of those pieces that contain chocolate, 22% had nuts. So that means we already know that they contain chocolate. So that's the condition. Given that they contain chocolate, 22% also contain nuts. So that means that the probability of having nuts, given that you contain chocolate, is 22%. That's given in the problem also. Then it goes on to read, of the pieces of candy that did not have chocolate. So now I'm conditioning on not having chocolate. So the condition is that you don't have chocolate. Of the pieces of candy that do not have chocolate, 9% contain nuts. So this is the probability of containing nuts, given that you didn't contain chocolates, and that's 9%, given as 9%. So some of these probabilities, these are the ones that are given. It says, let C be the event that the candy contains chocolate, and N be the event that the candy contains nuts. Oh, well, ahead of the game there. Find the following probabilities. Enter your answer as either decimals or fractions. Okay. Well, the probability of C, that was given, 0.41, that's a decimal. The probability of not C. Well, since C and not C are complements of each other, that means that not C, the probability of the complement of C is equal to 1 minus the probability of C. So the probability of not C then is 0.59. Let's see. The probability of nuts given chocolate, that was given directly as 0.22, right? And the probability of nuts given not chocolate was given as 0.09. 0.09. So all of that was given to us pretty much, except the probability of not containing chocolate. Then they ask us for the probability of chocolate given that you contain nuts. Now, the problem is the probability of a piece of candy containing chocolate given that it contains nuts, this probability is the inverted version of this probability. So anytime they give you one conditional and they ask you for the inverted version of that same conditional, you're probably going to be using Bayes. But we can start off with just a simple rule for conditional probability that says the probability of C given N is equal to the probability of C and N divided by the probability of N. So using that, we need to find the probability of C and N. Well, the probability of C and N is the probability of, let me see, that would be the probability of N, or the probability of C, I should say. That would be the probability of C times the probability of N, given that C has already occurred. And then that's going to be divided by, well, the probability of N, well, they don't give us the probability of N anywhere here either. But we have some things that we can use. We have the probability of C. We have the probability of N given C, so I know that amount of information. And then I want the probability of N. What I'm going to use is that the fact that the probability of N is the probability of N and C plus the probability of N and not C. The reason I'm changing it into a joint probability is because I have all these conditional probabilities and the respective probabilities of C and not C. So I should be able to find these joint probabilities by using the conditional probabilities and the marginals. So let's go ahead and try that out there. All right. So the top I already know, that's the probability of C times the probability of N given C. Well, the probability of C is 0.41, so that's 0.41, while the probability of N given C is 0.22, so that's 0.22, 0.22. And then in the denominator, I have there again the probability of C and N, the probability of N and C. Those are the same thing. Those are actually the same. So that's just going to be 0.41 times 0.22. And I just have to figure out what the probability of N and not C is. The probability of N and not C. Well, if I write it out the way this one is written, as a product of a marginal and a conditional, well, then let me do it in a different color here so we don't confuse it. That would mean that the probability of N and not C, C's complement, would be equal to then the probability of C's complement, which is something we have. We have the probability of C's complement as 0.59. But then we'd have to multiply that by the probability of N given C's complement. And, oh, we have that too. The probability of N given C's complement. So that's what I'm doing here. I'm doing the probability of N, or the probability of C's complement, which is 0.59, times the probability of N given C's complement, which is 0.09. So at the end of all this, we calculate these probabilities here. We do these products and everything. Let me see. On top there, I will have 0.41 times 0.22, which is 0.0902. On the bottom, I'll have the same thing, 0.0902, because those were the same. But then that's going to be plus that 0.59 times that 0.09, which is 0.0531. All right, bringing this home then, that means that the probability I'm looking for, which was the probability of C given N, is equal to, this is 0.0902 divided by 0.1433, which is equal to 0.6294. All right, so that's how we use the formula. You could have also used a tree diagram or a table.